Hi everybody! Today we're talking about orthogonal sets and bases with me today. Big idea is we want to know what happens when we use orthogonal vectors in our base. Quick reminder, what does orthogonal mean? So recall from last time, if we have two vectors in Rn, we say that they are perpendicular or orthogonal, because we are fancy people now, if their dot product is 0. Not the 0 vector, just plain 0, the scalar. Okay, so now we're going to talk about a set of vectors in Rn, and we would call this set an orthogonal set if every combination of v's in that set has a dot product of 0. You know, every combination except for where I equals j, because then you would be dot producting v1 with v1, and we know that that's not that's not orthogonal to itself. Okay, some quick examples. So we've got this first set in R3 is orthogonal. We actually know that. You guys proved that on your worksheet last time because I made you guys do every vector dot product combination. So thank you for doing the work. And then this set is also orthogonal, and that one's more obvious. Like if you dot product these guys, it's pretty easy to see that the dot product's going to be 0. And then same with these guys, they're going to be 0. So anyway, that's an orthogonal set as well. Fantastic orthogonal set. But anyway, why do we care? Because orthogonal sets make very nice bases. So that's our first theorem right here. We've got an orthogonal set of non-zero vectors in Rn. This set is linearly independent, and therefore, if it's linearly independent, of course it's going to form a basis for the space spanned by those vectors. So, in order to prove this, ask yourself, what is it that I'm trying to prove if I want to prove this theorem? I need to start with perpendicular and get to right here, linearly independent. Okay, so that's what we need to prove. Start off. So proof. I know that these guys are orthogonal. So are orthogonal. So what do we know about orthogonal? Let's keep it simple. I know things about orthogonal. I know that vi dot vj equals 0, so long as I doesn't equal j. That's a terrible 0. Okay. Where are we going? We are going towards linear independence. So we want to show linearly independent. What does that mean? How do we get linearly independent? That means we want C1, V1, and we need to add them up. We need to add up their linear combination. And if their linear combination is 0, they're linearly dependent if this only happens for the constants being 0 themselves. Okay, so let's start off. We're going to say, suppose that we have that linear combination. And then at this point, I would say try and pause the video. Like, hopefully I've talked you through how to think about setting it up. Pause the video, see if you can figure out where it's going to go. Okay. So suppose we've got the linear combination equal to 0. Over here, I'm going to just put a goal. C1 equals CP equals 0. All right, only thing we know. Dot product is 0, so let's go ahead and use it. Let's do V1 dot producted on both sides, because both sides are vectors, so we can do that. Okay. So what do we get? We know things about properties of dot products. We can move that inside our parentheses. We can get this guy. And then that's just going to be 0 on the other side. Okay, so what do we know from here? Well, we know that guy has to be 0 because we're back at orthogonal. But what about this term here? Well, we said non-zero vectors. So V1 is not 0, and we proved something about his dot product. That means his dot product's not going to be 0 either. So then in the end, like all the terms in here that I didn't write, those will all end up being 0 because V1 only matches with V1. So we get C1, and then this is V1 squared equals 0, where the length is not going to be 0. So then how is this thing equal to 0? Only way it can be equal to 0 is C1 equals 0. All right, so we got one of them. We've got one of the constants has to be 0. But really, we have more than that. If we repeat this process for each V, then we'll get each C is 0. So let's put that down in words by repeating this process for each VI. We get each CI equals 0, which is great. So now we have all of them are equal to 0. So C1 is equal to CP, which is equal to 0. And then what does that mean to have coefficients that are equal to 0? It means we have linear independence just like we wanted. Okay. So there we go. First theorem of the day, and we have proved it. So from here, we're going to say that we have a definition because I just said that the orthogonal sets imply linearly independent sets. So that means we're going to get bases from these orthogonal sets. So if we have a subspace V and it has a basis of orthogonal vectors, we're going to call it an orthogonal basis. Not so bad. So lemma 1, any collection of n orthogonal vectors in Rn form an orthogonal basis for Rn. Go ahead, pause the video. This is going to fall out really quickly if you use the theorem that we just used on the last page. Okay, so proof. So we know we started with any n collection of orthogonal vectors. So we know we have a collection of vectors that is orthogonal. And then by the last page, we now know that these guys are going to be linearly independent. But then we know things about this. Since they are in Rn, we are in the land of IMT, right? So span of n linearly independent vectors is equal to the entire space by IMT. He just won't go away. And so then by definition of basis, we get, oops, not a VP, VN. So this is a basis by definition of basis, because it was linearly independent and the span generated all of Rn. And then we already know it's all orthogonal. All right, so we have an orthogonal basis. Falls out pretty quickly from the last. I probably did more steps than necessary, but I really wanted to like break it down super slow. Okay, that brings us to the next thing. Remember I said stuff about like normalizing a vector. That meant we're going to take a vector and we can like normalize it so that it'll have length 1. So here we go. Now we're going to get a little bit more specific than orthogonal. We're going to talk about a set of vectors is orthonormal if it is an orthogonal set of unit vectors. So they have length 1 and they're all orthogonal to each other. We're going to call that orthonormal. I didn't bold that, and I apologize that. There we go. It's called orthonormal. Bold. Okay. So for example, got a couple of orthonormal sets for you guys. The very first one, we already talked about this like on the first page. Obviously, it's orthogonal. And then it's easy to see that like E1 dot E1 would just be 1 squared plus a bunch of zeros. And so you would get length 1. So they're all unit vectors too. And then this one, this is actually, I'm going to say, this is the orthonormal version of the set 1, 1, 1, -1. Like that. And we talked about him a little bit. He was one of our examples yesterday. So let's see. If I call this V1 right here, let's make sure that when we normalize it, we end up with what I just said that we're going to end up with. So V1, if we find the length of that, that's going to be 1 squared plus 1 squared root 2. So then 1 over root 2 times V1 is the same thing as root 2 over 2 V1, which is going to be root 2 over 2, root 2 over 2. And then obviously V2 over here, he's going to have the same length as V1, because when you square it, the negative goes away. So we will indeed get back to this guy. So yes, he has unit vectors, and we already talked about last time how these guys are going to be orthogonal to each other. So just shortening the vectors, which is all normalizing is not going to screw up the fact that they're orthogonal. Okay, so those are our examples of orthonormal sets. And you see how I went through and I normalized this vector set that we had already talked about? You can get an orthonormal set by normalizing any orthogonal set that you already have. So let's talk about that real quick. Oh man, and I didn't bold my definition again. So we've got V is a subspace. If it has a basis of orthogonal unit vectors, we call it an orthonormal basis. So that is our definition. That was not bolded again. I don't know what I was doing. I must have been really tired. Okay. So then why do we care about this? We're actually going to build orthonormal bases in 6.4. But for now, we can do some like smaller, less intense uses. They're really good in the columns of matrices. Why? I'll show you. First off, we've got a matrix U, and it has orthonormal columns if and only if, when you do this, you get the identity matrix. So let's go ahead. This is a more calculation intense proof and less of a thinking sort of a proof. So we're going to say that big U is equal to U1, U2, UN. And all of his little columns have length 1. So then UT, so U transpose, remember transposes take columns and turn them into rows. So we could say take the transpose of U1, which is column 1, and column 1 is going to become row 1 for U transpose. Okay. So that means column 2 is going to turn into row 2 if we just transpose it. Boop, boop, boop. All the way down to the end. Okay. So that's our guys right there. Let's go ahead and multiply them together, and I've left myself lots of room to do that. So we've got U transpose times U is equal to U1 transpose, U2 transpose, UN transpose, and then times U, which is just U1, U2, UN. Okay, so how do we get the first entry? Well, in a matrix, you just take the first column, remember this thing? You take the first row and you multiply them on top of each other. So here you go. First column, first row, it's shorthand notation, but we can multiply them together like this, and that's totally okay because our dimensions are going to match up. Let's see, this is, n by 1, and this one would be 1 by n. So they have to match in the middle, so we're good. And we do indeed get a scalar. Woohoo! So then the next entry, so if we wanted to go down our column, so first column, but second row would be first column, second row. So here you go. And then we can go all the way down to the last column, or last row, that's still in our first column. Okay. Now we're going to move to the second column. That means to get each row in the second column, we use each row here. So that'll be a U1 transpose now times U2. All right, and then we can go all the way out to the end. So now we're talking about the very last column. And then we have to do all these rows. Okay. And then remember what I talked about with dot product? I was like, we're gonna make up some multiplication, but really it ended up just being like the transpose of a vector times another vector. We can use that here. So this is the same thing as U1 dot U1. And then U2 dot U1 all the way down. So why is this useful for us? Why is this helpful? Because we know things about the dot products for the columns of U. We know that it's orthonormal. That means its columns are orthogonal. So that means that UI dot UJ equals 0 when they're not the same. So this entry, 0. This entry, 0. This entry, 0. Ba, ba, ba. But what about the diagonal? I need to make this smaller. Well, orthonormal also implies unit vectors. Remember that U1 dot U1 is really just this. But we know the length. We know the length is 1. Same for everybody else. So this is going to be 1, 1. So that means we're going to have 1s on the diagonal and 0s everywhere else. Sound familiar? This is just IN. There we go. Okay, so that's our proof for that guy. So that's pretty cool. So matrices with orthonormal columns preserve inner product data, which is why we're interested in them. They preserve like length, angles, and orthogonality, which summarized here in this theorem. So let's say we have an m by n matrix and it has orthonormal columns, and then we have these two vectors here in Rn. Then we get the following two properties. We get ux, or the norm of ux, equals just the norm of x. So u doesn't affect the length of x. And then when we have ux dot uy, we're just going to get x dot y. So it doesn't even affect the dot product. This is another more calculaty sort of a proof. And yeah, you guys should be able to like pause and hopefully get this done. So what does it mean? Well, norm means dot product of something with itself. Let's see. And then just like on the last page, dot product means that is the same thing as matrix multiplication, but with the transpose of the first vector. So like that. And then we know things about transposes. You just flip the order and we can distribute. Oop, no transpose here. There we go. But wait, we know things about U transpose times U. Oops. Okay. And then the I matrix just goes away, which means we can write that as dot product. But wait, that's just the norm. I messed this proof up. There should have been square roots on all these guys. There we go. Okay. Yeah. Because remember, norm equals the square root of x dot x. Sorry, please forgive me. And then number 2, it's actually very, very similar, which is why it's on your worksheet. So that'll be for you guys to delve into. And then it just occurred to me, if I seemed a little spacey, I'm going to rewind back real quick. I was just like, man, so shouldn't like U be, or UT be the inverse of U then? And I was like, man, I'm kind of trying to work through this while I'm working through the problem on the next page. No, U was not a square matrix, so no, it was not the inverse. And I'm going to point that out to you in case your brain runs down the same track mine did. But that's all I have for you guys today, and can't wait for you guys to prove this on the worksheet.